All right, again, good morning, everyone. Thank you for being here today for the RC design class. And we are going to finish the T-beam design. So as you can see that we have gone into the T-beam design a little bit. As people are popping in, quick review what we have done so far, right? So first of all, the difference between the T-beam and I-beam, first of all, is the definition or the geometry, right? So we need to know what is the section we're designing for. Okay, so to do that, there are two equations. One is for T-beam, you have this equation right here, and the other is for the L shape, which is the end of it, you have this equation here. So if I say that in the exam, you will be using these equations, I'm being completely honest, okay? You are needing these equations. So put them in a crib sheet or just label them on the ACI code and table 6.3.2.1, so you can use it whenever you need. All right, give it 5 minutes. It can be, yeah, okay, I see. All right, yes, sure, no problem, Megan. So here is the message as well to the Canvas folks. So we will know.
Done the homework for this class yet?
Sorry, Matthew.
Oh, my bad. I didn't realize I wasn't muted.
Oh, no worries. Don't worry about it. Okay, let's give 5 minutes, right? So we can probably just going around and see a
volume on this.
Okay.
Yeah, I think in the bottom of the
John.
I thought you were like teaching.
All right, let me try to do that. Okay, so here we have the continuous sections. All right, so you can see that. And we had a quiz last time determining what is the geometry for this one. And that is quiz 2, I believe. Yes, right here. So you can fill the number in for these base, which is 3 and 4. All right, and based on the equations we provided from last lectures. Okay, so that is for the T section, right? And once we determine the geometry, we can start talking about the stress distribution. Now, because it is a T-beam, so the stress distribution can be a little bit complicated. So why so complicated? Because now, once we have the T-beam, we have the web section and we have the wings, right? So the stress distribution in the wings and the web section are completely different. Why I'm saying that? Because if your A, which is the effective compressive zone size, that is bigger than the flange height HF, then you have two components, right? One is in the web that take the compressive zone size of A, effective compressive zone size that is in the A in the web, and then add it on the full flange. And when I say full flange, that is a flange fully developed, the stress of 0.85 at prime C here, 0.85 at prime C here, okay? Now, with that, that is so-called scenario number 2. Scenario number 2, okay? And scenario number 1 is that when A is smaller than HF, then you have a T section, but more like you have an I-beam, right? Because you have the compressor zone within the flange, so you can treat it as an I-beam. Right? So now you have scenario number 1, scenario number 2. So these two scenarios, we have to consider them separately. So now we took a look at the example and estimate the reinforcement ratio based on the scenario number 1, that is the effective compressive zone smaller than the flange height. We went along and play along, find out that actually no, the effective compressive zone is lighter than the flange height. Then we went to the scenario number 2. So from scenario number 2, we went through the whole calculation, assume the area and everything, and find out the moment from the flange and find out the remaining moment for the web, and went down, choose my bars, and eventually right at this section here, that is 8 number 9 bars, 8 number 9 bars, okay? Now, when I say 8 number 9 bars, I put them into 4 rows. Each row had 2 bars and lay them into the T section. And the question is, what is the moment capacity for this 8 number 9 bar reinforced T sections? All right, okay, so that's where we left at. Now, there were students asking me about how to calculate the distributed load in the simply supported beam, right? So that is, you can take the cross-section area directly multiplied by the specific weight of the concrete, which is 150 pounds per cubic foot, to get the distributed weight or distributed load in terms of pound per foot. as a linear distributed load on the span. And the reason is that we can take just the unit length, 1 foot along the beam direction, Okay. All right, so this is where we left at. And I noticed that since we're going to be online this month, unfortunately, I'm traveling. So I see that attendance is a little bit low. To encourage attendance, let's do this. We will still have online in-class quiz, but the quiz will be shorter, but the weight percentage will be a little bit higher since to encourage you guys to be attend online and see most of you folks.
Bob,
Yeah.
there's actually a bunch of us in the classroom right now.
Oh,
So
you're in
we're all on
classroom.
one
Oh,
Zoom,
okay.
but there's a lot of us here.
Wonderful, wonderful. How many students are in the classroom? Natalie, can you give me a count?
16.
Oh, that's good. That's good. So my apologies. Most of us are here, right? Were you guys be able to see the screen, anything like that?
Yeah, we can see the screen. It's up on the projector.
Okay, sounds good. And apologize for that, but still, let's do a quick in-class quiz on this, okay? Still, let's do that, right? To encourage the attendance, right? And also, since we're all here, might as well do a practice, okay? Now, the quiz number 4, that you were doing quiz number 3, that is on this T section, right? So quiz number 4 would be that I have a simply supported beam, okay? And this will not take more than 5 minutes for you guys to do, okay? I have a simply supported beam. And I have a section in the beam that varying section. So let's call it 4.1. I have a rectangular section. And this is 12-inch. And this is 14-inch. All right, I want us to convert this in terms of distributed load, omega, using the same method I just described here, omega, okay, into the distributed load. And note that the unit for that will be pound per feet. Pound per feet. Okay, and so this was the first one. And the second one, I want us to do a T-beam. Just like what we have here. So this is 47-inch, and this is 11-inch, and this is 3-inch, and this is 20-inch. So what will be the omega right here? Okay. All right. I'm going to give you guys, let's say 3 minutes, right? So 3 minutes, and we can compare answers. And what we'll do is you guys will perform the calculation, and I'll go alphabetically, pick my victims, and I call them out and provide some numbers, right? And we can compare and finalize that. And you can, right after class, I'm going to create quiz number 4. You can just fill the number. You don't have to fill in the calculation process. Just fill the number in the quiz. So we'll have the extra credits for the quiz. All right. So how about that? So let's start right now, 9:09 right now the time is. So I will start calling out for numbers around 9:12. Okay. All right. So simply just calculate what will be the distributed load for rectangular section 4.1 and for T-beam section like this. Okay. One is a little bit stocky. Okay. 12 and sorry, this is not 14, 24. Okay. Apologize. 24. Okay. 1 and by 2. Okay. The other is 47-inch, 3-inch, 20-inch, and 11-inch. All right. Okay. So time starts now. All right, I'm gonna go get myself some water, and I see you in 3 minutes. Okay.
Real quick.
Yeah.
So are you saying we're converting the weight into a distributed load?
Well, yeah, self-weight, right? So self-weight of concrete only to the distributed load. Does that make sense? Steel bridge?
Yes.
Okay. All right. Okay. I'll see you in a few minutes. Okay, I know you're still working on it, but when you do the calculation, just be careful, okay? Area and weight, right? Area and wood, and everything want to convert back to pound per foot, all right? Pound per foot. Okay, so area multiplied by the weight and pound per foot. Okay. All right, and Natalie, I know you have 16 friends there in classroom. So later I'm gonna call you and you can give me some numbers from your friends. How's that sound? That sounds all right?
Sounds good.
Okay, thank you so much. All righty. Okay, I think the time's up. Let's start from the online audience, right? Let's see what number you get. So I'm gonna start calling my victim here. See who's here, who's here. How about Steelbridge? Steelbridge, you were asking a question, sir. How are you doing, sir?
I'm doing great. How about you?
Good, good, good. So can I get an answer for rectangular beam?
Yes, I'm getting 300 pounds per foot.
300 pounds per foot. Wonderful. Okay, that is a easy one, right? 300 pounds per foot, that is correct. Okay, and Natalie, can I get a number from you folks on this T-beam shape?
Same thing. I think it's the same weight, 300 pounds per foot.
That's for the rectangular beam, right? Or that's for the T-beam?
Oh, no, for the TV.
Yeah.
I don't think anybody has it yet.
Okay, let's wait a little bit. Let's try my audience here. Okay, Bo. Mr.
Yeah, hello.
Hey, how are you doing, man?
Good, how are you?
Not too bad. So have you ever got a number for my T-beam here?
Yeah,
Okay, what you have?
167.71.
167.71.
71.
All right, good deal. Okay. Natalie, anybody? Same number, different number?
Yeah, we got the same number.
Okay, so that sounds right. So yes, indeed. So that is the dead load exerted on the beam, right? So one is 300 pounds per foot and the other's 167 pounds per foot. So that is the dead load. Now this is 4.1, 4.2, right? Now my question is, if I were to design it, right? I say that this is the beam. So this beam will have soft weight. Okay, and let's just say that it will have a soft weight of a T shape. So that is to say that omega D equal to 167. Let's just ignore the 0.71, right? To make a wholesome number easier for me, 1.68 pound per foot. Okay, so that is the dead load. And I say that, and a live load of omega L 1.2 kip pound per foot. All right, and what will be my design, or sorry, not design, but factored or required moment for the beam? And given that the span length of the beam, and let's just give this some number here, center to center, and my horrible drawing right here, but L equal to 20 feet. All right, L equal to 20 feet. All right, so to solve this problem, let's call it 4.3. All right, all we need to do is omega, sorry, mu equal to, what is the moment equation for mu? Austin, Eisterhold, Mr. Eisterhold, are you there? Hey, how are you doing, man?
Good. How are you?
Good, good, good. So what is the moment for simply supported beam? So S simply supported beam, right?
1.2 dead plus 1.6 live.
Sure, 1.2 dead MD plus 1.6 live ML. That's correct. Now, where I'm having you here, so how about the moment equation in terms of MD? That is what?
Moment in terms of MD would be the
Give you a hint.
sorry, I'm blanking on the word, the distributed load times
Right,
the distance from center, so 10 feet.
right. No, wait. Do you see my screen here?
Oh yeah.
Right, right. So 1/8.
8.
There you go. Omega D and
The length
L
cubed. Or
Square, close, okay?
Sorry, I was
Square,
close.
okay, that's correct, okay? So that is the moment for distributed load. And now that is 1/8. And I got omega D is 167. And now I want to convert everything back to kip foot, okay? Folks, I want everything back to kip foot. So this is 0.167, let's say 1.68, and multiply 20 feet squared. And Natalie, can you guys help me out? Let's punch some number right here. Any number from your 16 strong there? Any number shout out from your 16 strong there? And while I'm waiting,
8.4.
8.4. That's it.
Yeah.
All right. So that is hip foot. And thank you for shutting down the echo there. And let me find another student, Jacob. Mr. Stratman, are you there?
Yep, I'm here.
Hey, how are you doing, buddy?
I'm doing fine.
All right, good deal. So do you like this number? What the other 16 students find out? 8.4 kip foot.
Yes.
You get the same?
Yeah, I got that too.
Good deal, good deal. Now, while I'm having you here, can you help me out here? So this is 1/8 omega L squared, so 1/8. Live load is 1.2 and 20 feet squared. Can you move your finger in the flashing speed? Let me know what you have here.
Yeah, 1 sec.
So while you're working on it, let me just go ahead, get the number out. 400 divided by 8 was 1.2.
All right, I got 60.
60
feet.
feet. There you go. That's the correct answer. Thank you, Jacob. All right. So now that is my applied moment from dead load, from live load. And now finally the factored moment. Factor moment. All right, let me see who's there. Megan. Megan, how are you doing?
I'm good. How are you?
Not too bad. Thank you for being here in the classroom. And so this is 1.2 multiplied by 8.4 plus 1.6 multiplied by 60. Can you help me out to get a final number on the thing? 1.2, 8.4, 1.6, 60. That's like 96 plus something.
$106.08.
106.0.
8.
All right. Wonderful. So that is 106.08. So this is about 10.08. And that is my applied or factored bending moment. Okay. All right, guys. So that is how we're going to get the factor moment. So if I were to design this, right, this will be my factored moment for design, factor moment for design. Okay, so now where I'm having this, right, you may wonder, why am I spending so much time on it? Because now that was a simply supported beam. Say, if I'm going to switch the boundary condition into a cantilever beam and have a force pushing down here, say this is PL, and that is a 12 feet. Okay, I don't do dead load. I just want to do this live load thing. Okay, and I say that might as well just adding another dead load onto it. All right, and if I say that the live load is 10 kip foot. Okay, live load is 10 kip foot, and I say that phi that is my design moment. Okay, design moment is about 200 kip foot. When everything's said and done, okay, my design moment, that is after strength reduction factor, after nominal strength is 200 kip foot. Okay, what will be the maximum soft weight? Or I shouldn't say soft weight because dead load include other things as well. So maximum dead load. Dead load can be applied to the beam. Okay, so that is to find out my PD. Okay, now how to solve this fellow right here? How to solve this fellow here? So you look at this problem, you say, well, I don't know how to solve it, but I know that design equation reads Vmn has to be greater than or equal to mu, and that is 1.2 md plus 1.6 ml, and that is 1.2 pd multiply 12 feet plus 1.6 p live, that is 10 kip foot multiply 12 feet, right? Because that is the cantilever thing, right? So now I have on the left-hand side is 200 kip foot, right-hand side, this fellow here. So PD would equal to 200 minus 1.6, so 60 minus, so sorry, 16 minus 12, multiplied by 12, and divided by 1.2, multiplied by 12 feet. So now that would be my dead load can be exerted on the beam. Now, Matthew, Mr. Jensen, are you there? Matthew,
Yeah, I'm here.
hey, how are you, buddy?
I'm good. How are you?
Not too bad. So can you help me out? Get this number out for me? The
Yeah,
dead
I'm
load
punching
on
the
it?
numbers right now.
Okay, 200 minus 16, another 12, divided by this. So I'm just gonna
I got 0.833.
0.833. Okay. No foot, just kip. Okay, so that, ladies and gentlemen, is the number we get. Anybody get different? Anybody get different?
I got 0.55.
0.55. Okay, anybody get different?
I also got 0.55.
Alrighty, so I'm sorry, Matthew, check your number. Majority says 0.55 wins, okay? So let's check this number, okay? All right, anybody else? Anybody else? Maybe I read it wrong, but let's go with majority number, okay? Let me quickly do this real quick. So this is 12 to 1.6. Yeah, I think this is close to that, okay? All right, so now that is my dead load. Okay, all right, so you look at this problem, you say, Bob, why are you doing this beginning of class? We were expecting to do T-beam, and why are you doing this? Because in the last year's exam, most of my problems, most of the errors students made are these structure problems. It's how to calculate the moment, okay? For dead load, this is, for now, for distributed load, this is the equation. For a cantilever, you use this part, okay? Now, last question for this part, okay? I'm going to talk more about next Tuesday, but right now, as we're at it, right? So last question about this part. If I were to make this into reality, right? Make this into reality. This is simplified drawing, making this into reality. So now I have my boundary condition set like this in the three-dimensional drawing showing like that, right? That is my plate, end plate. And my beam, say if this is a, what do we call it, T-beam, right? So it looks like this. T-beam look like this, okay? And I draw like that. Horrible drawing, but you get a drift, right? That is my T-beam. Okay, so this is so-called A. And let's call it scenario A. I like the word scenario too much, I guess. Forgive me on that. But let's say that I flipped the boundary condition, right? I have another alternative. Is that I'm going to put the beam like this. Flip it down, right? Flip it downward. Okay, and that is my flange is going to be the bottom side of it. And my web is on top. Okay, again, my drawing is horrible, but I'm no Picasso. Or maybe I am, right? It's very abstract. So let's call it scenario number B here. All right. I'm going to pick my next victim, okay? So knowing that my condition is a cantilever, okay? My condition is a cantilever, and my beam or my load is at the end of it and pushing downwards. And let me spell it out for you even better, right? So that is to say that my bending moment here is negative, okay? Negative bending moment mu here equal to this, voila, what is this? 200 kip foot, right? 200 kip foot. Voila, okay, negative bending moment. Let me say it again, negative bending moment, okay? When you design the beam, will you install the beam in like scenario A, or will you install the beam like scenario B? Which one you pick, A or B? Let me find my next victim. Okay, what are you thinking? Nathaniel, are you there?
Yeah, I'm here.
Hey, how are you?
I was good until you called on me.
Well, that's the fact, right? That's the fact. All right, well, you're on the spot now, sir. So which one you pick, A or B?
I'm gonna go with B because it's negative.
All righty, that's actually the interesting answer, okay? And Natalie, with your 16 folks strong there, do you guys have a consensus?
B, I
Yeah,
would say.
that's right. That's right. Wonderful. Okay, so that is my answer, which is B. Okay, now to emphasize on this, make it even more interesting, right? I'm gonna say if switch to a rectangular beam, rectangular section, all right? If switch to the rectangular section, that means my end support still like this, and my beam looks like this. And I have my rectangular section. Now there's no upside down, right? There's nothing called direction, right? Same thing, A and B, whatever, right? So let's call it A and B again. And they look the same. No matter I put it up or I put it down, they look the same, identical, right? Just a old-fashioned rectangular beam. But now the question is, I draw the cross section, right? A is my reinforcement here on top. Note that, okay? Tensile reinforcement only, okay? Single layer reinforcement only, okay? And B is my reinforcement at the bottom right here. Question is, which one is correct? A or B? A or B, okay? Which one's correct, A or B, okay? Let me pick my next victim. Benefits of less people, you can call them all out, right? Ryan Huskin. Ryan Huskin. You there? Hello, Ryan? You sleeper? Sleeper? Problem with the microphone? Okay, let me try next. Ryan, right. Ryan, right.
Hello.
Hey, how are you doing?
Good. How are you?
Not too bad. I'm in the pickle right here, Ryan. So I have my case that A or B, reinforcement A in the top, reinforcement B in the bottom. Which one will you pick?
I would pick B, I think.
Okay, so Ryan opt for B, okay? I'm just gonna put a question mark here, okay? And let's see, Natalie, I keep calling you, I'm sorry, okay? You become an extra representative for your 16 people there. But can you collect your consensus of which one you will pick, A or B?
We're going with A.
You're going with A, so the majority goes to A. And I'm just gonna put a face here, okay, right? And now, why? Why is A, Natalie? Where are you at here?
Because the tension's at the top.
Tensions on the top, that's absolutely right. Thank you so much, Natalie. That's it. Okay, that's it. Okay, so Megan actually replied, sorry about that. Okay, I saw that now. Okay, good. So this is the exam number 1. Okay, that is the tricks in exam number 1, right? So same thing actually for the T-beam. If you really look at it, right? If I really want to look at it, I have here, and Ryan, take a look at this, right? So if I have A, which means my reinforcement gonna be at the bottom, right? Gonna be at the bottom. But if I have B, my reinforcement is gonna be on top, isn't it? My reinforcement is gonna be on top. Okay, so that's why for the first problem, you choose B. The second problem, you choose A. Only reason is that because the tension side is on the top. Tension side is on the top. Okay, all right, folks. This is everything I want to say about the load distribution and some of the tricks you might see in exam number 1. Okay, so for you, all your score or credit wise, just get this number filled. You don't have to show the process since everything's in the notes. I just want you to fill this number, and fill this number, and fill this number, and to the quiz number 4, okay? Let me just label them out, okay? Fill these numbers, quiz number 4, just show that you're here today, okay? You're here today, okay? All right, and that is everything we need to do for quiz number 4, okay? Quiz number 4. Okay, so now with all the structure things, housekeeping things taken care of, let's circle back to look at the problem, quiz number 3, okay? If you haven't submitted, don't worry. We're going to go over them a little bit today, okay? And if you have done that already, congratulations. You have learned quite a bit and you can now compare your results with mine. And keep in mind that my results may not be the only results or correct solutions, okay? Your results might also work, okay? So how to judge, this is how we're gonna do it. So now get back to the T-beam design, okay? So going back to the T-beam, I'm just gonna put a division line here. So T-beam. We are looking at a section like this, and we say that now we already selected 8 number 9 bars. So 1, 2, 3, 4, 5, 6, 7, 8. And we know that already, no matter how I'm going to do that, there's going to be 20 inch of depth right here, 20 inch of depth right here, and that is my DS. And I fix that, okay? No matter what I do, I have to maintain that, to satisfy that. Right? So solve this problem, several things we need to do. First is that we have to do assume, right? Assumption, assume scenario number 1. What is scenario number 1, you may ask? That is the compressor size A is smaller than the HF, right? The lucky one. When I say that, that means that my T-beam behaves like 9 section rectangular, sections of T, treat as a rectangular section. All right, it's for scenario number 1. So when I have that, I say, okay, so that means all my compressor zones right here. So all my concrete compression is coming from the flange. So CC is actually from the flange, and CC1 equal to 0.85 F prime C A B E. Okay, E, that is the total width of the flange. All right, for those folks, if you're not aware of or forgot about it, BE equal to BW, which is the web, plus 2BF, okay, the flange width. And now ASFY, which is the tension force, because everything is just staying in the flange, so I don't have to split my reinforcement anymore, and that is equal to 0.85 F prime C ABE. Okay, now following this thought, I can directly find my A, because I assume that A is smaller than HF, right? So quickly, A equal to ASFY divided by 0.85 F prime C BE, and ASFY is 8 inch squared multiplied by 60 KSI and divided by a 0.85, and F prime C is 3 KSI, low grade concrete for this one, right? And 47 inch of width. All right, so now you have a number and save you the trouble, and that is unfortunately 4 inch. Unfortunately, 4 inch. Why I say that? Because remember, the assumption is it is smaller than HF and no longer hold, so no good. No good, okay? No good. So now I'm forced to go back to scenario number 2. Scenario number 2. So when scenario number 2, I don't know A, but I know that A is greater than HF. So I don't have to draw the tiny drawing for you again. You know that I have to split the section. Well, if you're forcing me to do that, I can do that, split the section into the wings, right? The wings plus the web, right? So that is how we're going to do that, right? So with that happen, I have known that CC1, that is the concrete compression from the flange, should equal to 0.85 F prime C HF, because it's fully developed, right? That's the 1, and this is 2, okay? This is flange. Let me just label here so you can see it better. And this is web, it's HF, and now be careful, this is only the flange, so that is BE minus BW. BE minus BW, right? So you write it out, CC1 equal to 0.85, bring the number in 3 KSI, 3 inch, and BE 47 inch minus BW 11 inch. So that is my number, okay? And now I have my total compression force about 275.4 kips. Okay, save you the trouble. Okay, so that is for the flange, all right? And mind you that if I say this is for flange 1, so I know my reinforcement has to be split into 1 and 2, and for the reinforcement for the flange equal to CC1 divided by AS1 FY, so divided by FY. So that is 275.4 typos kip divided by a 60 KSI. So I know my reinforcement area required for the flange is 4.59 inch squared. All right, now you know that we selected, right? We already selected the bar, so there are 8 number 9 bars. So if AS1 equal to 4.59, AS2 equal to 8 minus 4.59 inch squared, and that is a 3.41 inch squared. Okay, so with that, I say, look, now I can talk about my web here. And my web has this tiny thing here. This is A, this is BW, which is 11 inch, by the way. So my job is to find A, right? So A should equal to T, which is AS2 FY, divided by 0.85 F prime C BW, because this is the web, right? You bring the number 3.41 inch squared multiplied by F1 FY 60 KSI divided by 0.85 F prime 3 KSI and multiplied by a BW that is 11 inch. All right, and A equal to a 7.29 inch. All right, so that is my A, and just where you add it, you say that is bingo, very good. Why is that? Because A now is indeed bigger than 3 inch. So, okay, my second assumption, scenario number 2, of course, stands. All right, okay. Now, everything should be done now, right? You look at the section, you say, finally, I have a beautiful T section, and my T section has the compressive zone size of A and have the flange fully developed, and this is 7.29 inch, A equal to 7.29 inch. And now BE is 47, nice and easy. And BW is 11 inch where I'm at it, and that is my compressive zone. Very happy. So with that, I started drawing my strain diagram. We haven't seen this before, right? First time ever, because this is for the T section. Anything different from rectangular section? No, same deal, right? So the compressive strain in the concrete remains 0.003, and now the tensile strain is somewhere here at the center of it. I don't know that. All I know is that the depth is 20 inch. If the depth is 20 inch, and if I know C, which is the actual compressive zone, I should know the strain in the steel. Why do I need the strain in the steel? Why do I need the strain in the steel? And why do I need a strain in the steel? Because 2 things. I need to check whether it's yielded, or I also need to check another thing is epsilon T right here, isn't it? I need to check the strength reduction factor phi there. Okay, long story short, C should equal to A divided by beta 1. All right, and now I know that beta 1 is actually something here. So 7.29 inch divided by beta 1. So I'm gonna pick somebody help me out here because I kind of forgot. Blake, Mr. Elder.
Yeah,
Hey, how are you doing, buddy?
I'm doing pretty good.
Good to hear. So can you help me out here? Beta 1 value here. And mind you that for a concrete of prime C equal to 3 KSI, do you remember the number for it?
Isn't that 0.8?
0.8. Sounds right to everybody else? Anybody get a different number? Anybody? Dead silent?
0.85.
0.85. Natalie? Anybody?
Second to 0.85.
Actually, I think
it is
0.85.
I got a second. Okay. All right. So that is the correct answer, 0.85. Okay. Why is that? Because beta 1 at prime C, and this is 0.85, as long as it's lower than 4 KSI, and that is 8 KSI, and this becomes 0.65. Okay. So 0.85. Correct. All right, good deal. Okay, continue. So now C should equal to this divided by 0.85. And Blake, can you help me finish this at least? 7.29 divided by 0.85.
I got 8.58.
8.58, great. Anybody different? Anybody different? Concur? Anybody? Come on.
Got the same.
Same, good deal. Okay, so 8.58, nice. So with that, I can proceed. I say, all right, fine. Epsilon s equal to ds minus c over c multiply epsilon cu. ds is 20 inch. C is 8.58. That's right. Divided by c, which is 8.58 again, and multiply 0.003. And I got this number to be 0.0039. Save with the trouble. And when I see that number, should I be happy or sad? Aubrey, Caldwell, Aubrey.
Hi.
Should I be happy with it? Or are you, by the way?
It's less than it's in between 0.002 but less than 0.005, so it's in the
Wonderful.
transition zone, but still under reinforced. So
Wonderful.
like it's okay, but not great.
Exactly. Thank you so much for the information, Audrey. That's absolutely correct. So it is half-half. I'm half happy because it yielded. So yielded, sure, but it's not tension controlled. It's not tension controlled. All right. But you know that we're not calling it out whether it's tension control or not using epsilon s. We are using epsilon t. Okay, so we have to use my epsilon t value dt minus c over c multiply epsilon cu. All right, and we only know that epsilon s is 20 inches, right? I don't know dt. So how am I going to determine dt? I'm just going to say that maybe dt approximately equal to a height h minus 3.5 inch of bars, right? So if I do that, I'm going to have a problem. Why is that? Because h is what? 23 inch minus 3.5. I end up with 19.5 inch. What does that mean? It means that my dt is actually smaller than ds. Oops. Oops. So what does that mean? It means that if I have my bars situated 8 bars, I'm just going to exaggerate, okay? I'm just going to exaggerate. So let me put these 8 bars out first, okay? And I say, let's zoom in, right? Let's take a look at it. And now I take a look at it. So 8 bars, right? So 1, 2, 1, 2, 1. Sorry, let me just move down here a little bit, okay? 8 bars right here, okay? And now I said the height, whatever that might be, at the center of the group of bars is not exactly here, but somewhere in the middle line, lower than that, somewhere here, and that is the s equal to 20 inches. And you telling me if I have multiple bars, I use the approximation h minus the concrete cover, I end up with a dt that is where? That is somewhere even higher? Oh, that doesn't make sense, does it? No, it doesn't make sense, sir. It doesn't. Okay. Now, what do we do? What do we do? And first of all, what's wrong with it? What's wrong with that is that basically you have too many rows, isn't it? Your bars are too stacked too high that you end up have a problem that your centroid cannot be spaced enough, so you don't have enough concrete cover. So that means if you put 8 bars in 4 rows, you simply cannot fit it into the section and has the s equal to 20 inches. That's simply not possible. That's simply not possible. Okay, so what we're going to do is that we are having a problem, so we're going to reconfigure the reinforcement. I say that now I have to reconfigure. Okay, and I have to force myself to reconfigure into 3 bars in a row. 1, 2, 3, 1, 2, 3, and 2 extra on the side. All right, so hopefully this will work. Okay, hopefully this will work. Okay, and say if I can make this work and somehow I can still maintain my 20 inch of depth. Okay, if I can still maintain my 20 inch of depth, and I can assume that maybe from the centroid of the bars to this bottom bars, and approximately 2 inch of spacing, and this is purely assumption, and with added 1.5 inch of a concrete cover, I end up with dt of ds plus 2 inches. So dt roughly equal to 22 inch. after reconfiguration. 3 rows, 3 bars in a row, 2 row, 2.5 row, right? So that is what I'm going to do. Okay, so quiz number 5 is to check my configuration, okay? Check detailing to see if this is going to work. Now, specifically, 2 things. I just wanted 2 questions. For 5.1 question is BW wide enough? All right, so that means can BW 11 inches accommodate this 3 bars or not? So I just need a yes or no answer, okay? Yes or no answer. And second question, can I put this into the section and maintain that and make sure my DT is greater than DS? Again, this is yes or no, okay? Try yourself, okay? It may not be yes to both answers, okay? All right, so this is quiz number 5, okay? Quiz number 5. All right, now, let's just assume that everything worked out, okay? You guys did the quiz, and by Thursday, which is tomorrow, we're gonna figure out, and we say that, look, everything's gonna be fine. Everything looked nicely. And now we say, look, all right, here is the DT. And I say that it is just 22 inches. Don't care why I snatched the number, but this is DT. All right, and with that, I'm going to bring down to the stress reduction factor phi with known epsilon t, and epsilon t should equal to what? Epsilon t should equal to dt minus c over c multiplied epsilon cu, and 22 inch minus c, which is 8.58, and divided by 8.58, and multiply 0.003. And save you the trouble, I calculate this one to be 0.047. And like Aubrey said, this is bad again. It's not tension control, which is 0.05. But that's okay. I'm just going to bring this number in because I know the equation for phi, and phi goes like this, somewhere like this, right? And this is 0.005, 0.002, and this 0.65 and 0.9. So I am going with this, and I say that phi equal to 0.65 plus 250 over 3, and multiply by epsilon t minus 0.002. So phi, bring the number in, equal to a 0.87. Okay. And now with that, I say in 1 minute, bear with me, folks, mu equal to AS1 Fy and ds minus HF over 2 plus AS2 Fy and ds minus half A. 2 moments, okay? Flange and web. I cannot stress enough. You have to have both, right? So Mn, not mu, Mn equal to a number. I'm just gonna calculate it straight out, and you can do it yourself. That is 703 kfoot. So phi Mn equal to 0.87 plus multiply 703. So I have a 611 kfoot, which is greater than mu, which is 533 kfoot. You forgot, but this is the number I was given, okay? So design done. All right, folks, this is it. This is your quiz number 3, okay? If you remember, this is quiz number 3, okay? All right, so thank you very much. We're done with today's lecture. Thursday, which is tomorrow, we're gonna go into irregular sections, okay? And I will leave the homework on Thursday. And stay behind if you have any problems or homework questions about it, okay? We'll talk about it. Other than that, thank you so much. And you see this video upload to YouTube today. All right, thank you. Bye now.